Hi, this is Ojas Parekh, and I'm going to be talking about provable neuromorphic advantages. The kind of practical driver behind this work is that many vendors have started offering neuromorphic computing devices with millions to billions of massively parallel artificial neurons. So current generation systems are expected to offer 50 to 100 million neurons this year, and then in the next few years, we expect systems with 1 billion neurons. The idea here is that neurons are much more specialized computing devices, and so you get better trade-off in parallelism. Communication is sort of less of a bottleneck, and it is easier to kind of construct networks of massively parallel neurons. So since hardware platforms essentially offer such networks, a natural idea is if we can employ them for graph algorithms. Another kind of driver here is that there are virtually no theoretical results about neuromorphic systems. It's a fairly recent development, and it's mainly been motivated by learning-oriented applications. In a 2017 survey by Schumann and co-authors, they covered sort of a wide swath of neuromorphic computing, a comprehensive sort of survey of hardware, software, algorithms, applications, and in compiling over 2,500 sort of references, there were only a handful of what you might call graph applications. And even then, most of those had a learning-oriented component. Recently, a few more traditional graph algorithms papers have emerged looking at things like shortest paths, but theoretical models are still limited, and sort of rigorous analysis of these algorithms and moreover comparison with conventional algorithms are virtually non-existent. So this is what we address in this work, and more generally, we feel this is a timely opportunity for the theory community. So neuromorphic algorithms, specifically here we're talking about algorithms on networks of spiking neurons, employ the leaky integrate and fire neuron. This is sort of the model we use, the model used by many of the works mentioned. It's sort of a fairly simple but robust model that is thought to capture how neurons in the brain work at a high level. Sort of a static version of this model employs what are called threshold gates, and you might be familiar with those from neural networks, where you have a weighted combination of binary inputs, and there's an internal threshold within each neuron, and if the weighted sum sort of exceeds the threshold, then the neuron fires. Here we're looking at a temporal version of this, where there are incoming signals and outgoing signals, and sort of these networks can have loops and recurrence, and there needs to be a notion of when the computation starts and when the computation ends. Moreover, in the leaky integrate and fire model, there's sort of an internal potential that decays over time that has a memory effect. That's also a powerful feature for algorithms that we employ in many of our algorithms. So a simple example of an elegant application of such a model is just computing shortest paths, actually. So here we just assume non-negative edge weights, and we can see that actually you can implement Dijkstra's algorithm neuromorphically in a very natural way. So the idea is that the neurons here are configured to simply propagate an incoming signal. And we started spikes, these yellow circles, at the source, and the first time a spike reaches a node, the time at which that happens is proportional to the length of the shortest path. So you could see that spikes that followed this red path were the ones to reach the sink first, and that corresponds to the shortest path. So you can augment this algorithm to actually keep track of the shortest path as well, but one feature here, or actually one kind of limitation here, is that this is a pseudo-polynomial time algorithm because the running time actually is proportional to the length of the shortest path. So our work kind of remedies this by coming up with truly polynomial time algorithms that give a provable advantage over conventional algorithms. The problem we look at is the k-hop shortest path problem, where one is still interested in a minimum weight path between two nodes in a non-negative weighted graph, but here we're allowed to use at most k edges in such paths. So the conventional, a conventional algorithm such as Floyd-Warshall gives you a running time of km, ignoring log factors. Our neuromorphic implementation has a running time of k, so k basic steps. One challenge here is that neuromorphic systems operate sort of vastly different from conventional models, in the spiking regime. And so comparison becomes kind of difficult. And a lot of our work is sort of establishing how we can fairly do this comparison kind of end-to-end, taking all factors into account. So one thing that's not satisfying about the aforementioned result is that this kind of assumes on the neuromorphic side that your input graph can be mapped exactly onto neuromorphic hardware. To remedy this, we have other results that kind of only assume a very simple neuromorphic hardware graph that's sort of grid-like. It's called a crossbar. And so then if you'd like to solve shortest path problems on a domain graph, it needs to be mapped into the crossbar. So when we take that kind of embedding into account, this adds an extra multiplicative factor of m. However, this kind of embedding, what this points to is this is sort of accounting for data movement on the neuromorphic side. We don't get to send spikes across the network for free. We sort of have to embed and pay for them. So for a fair comparison, we feel that data movement also needs to be taken account on the conventional side, and we develop a sort of kind of a intra-chip model of data movement. So a fine-grained model of data movement within an SRAM or a DRAM. So the main idea that we're putting forth is that although neuromorphic systems are kind of massively parallel, they ought to be compared with serial CPUs. And the evidence for that is that current generation neuromorphic systems have anywhere from 100,000 to 1 million neurons per chip, whereas conventional CPUs have maybe 8 to 32 cores, maybe 64 or so in kind of high-end chips. But nonetheless, this is sort of hampered by Moore's law, and in some sense, this is a constant. Whereas neuromorphic, we being kind of engineers and hardware developers, feel that there's potential for growth, and it's touted as a beyond more technology, where the adult human brain has 100 billion neurons. So the idea is that we're comparing neuromorphic systems with single CPUs, and then we need to look at data movement within a single CPU. And so this is sort of the basis of our data movement model. More details are in our paper, and thanks for your attention.